Well, hello, and welcome back. Pop top, my friends. Let's have a little word from Mr. Mountain Dew here. Wait, let's listen. Oh, there it is. What was I going to say? Yeah, Revenge of the Benchmark. Okay, so a couple of things. One, so I had Duncan on. He helped explain a interview problem that I had trouble understanding because as I said before, I have a real hard time understanding not just contrived problems, but misleading problems. Problems where they give you a false context, and I don't know what the purpose of this is. It certainly doesn't make it easier to understand anything, and maybe that's the point. I don't know. But so this problem has this false context of being something about football, when obviously it is nothing to do with football. We'll get back into that in a second. I'll give a brief overview of it. But what I was going to say is two things. One of the problems with these interview problems is that they don't give you this right here. When you encounter a real problem in the real world, you tend to work on it for a little bit, and then you walk away from it. And then while you're walking away from it, your brain's still keeping track of it and kind of processing and letting things settle in the subconscious. And then when you come back to the problem, you can come back with better solutions. So these are from, this is from the Go authors. This is one of my favorite blog articles of all time in all of history. And it says, in regards to a problem that they had that they didn't know the solution for, that it says, we did what we always do when there's a problem without a clear solution. We waited. Full stop. Waiting gives us more time to add experience and understanding of a problem, and also more time to find a good solution. So, this is, now that I've stepped away from this problem for a little bit, despite the fact that it's a contrived problem and it's not real, I think I have some better ideas for how to solve it because I was able to let it settle in my brain. So here is the actual problem. Is that too big? It might be a little too big. Yeah. This was the problem that we started with. Basically, I'm going to try to recite it again in 30 seconds or less. You're getting two lists. One, I'm not going to read what it says here because it's completely misleading. You're getting two lists. You're getting a list of reference values and a list of inputs. And what you're asked to do is, for every value in the list of reference values, give back the number of values in the input list that is less than the reference value, which means that if you're counting values less than 5, less than or equal to 5, you're going to get some subset of the inputs. Say there's 4 of them that are numbers that are less than or equal to 5. And then if the next number in the reference list is 6, then you're including all of the ones that were less than or equal to 5, but you're also including the additional ones that are less than or equal to 6. Yes, the best solution comes on the way to the bathroom. It's so true. Thank you for that, Kirglo. All right. So that's what the problem is. And here's the part that got me just fuming about this. Not fuming, that's not the right word, but just feeling a little, I'm the expert on this channel. My solution's going to be better than your naive whatchamadoo hickey, right? So let me see if I can bring this over here so you can see. So what's the impetus for this? Where I can't just leave this alone and go on to something else that's more important to my life and everyone else's, hopefully, is that Duncan says, hey, I just tried this for 1 million entries, and look, here's his faster reduce, which, by the way, I'm gonna nitpick it at him on the use of reduce. We're gonna go into that in a bit. And then here's AJ. I don't have the right sound effect for this, but that's the best that I got. How could the master produce a solution that is so suboptimal? So we're going to, first of all, we're going to take a peek at why I think that my solution ran so much slower. And then we'll see if I might want to benchmark his, we're going to benchmark his solution as well, because we're actually going to take a peek at his solution, and I'm going to see if I understand it clearly and give some nitpicks on it. Basically, anytime somebody's using reduce, you can just assume that they're doing it wrong. Because, well, reduce, people just use reduce as kind of a catch-all for loop rather than just using a regular for loop, and it ends up being more complex and more difficult to read and whatever. But we'll get into that when we get into that. And no offense to Duncan, because he found a solution that apparently is better than mine. But this is what we're going to do. So I'm using his scores generator function that he provided to me on Discord. And I am going to replicate his test, and I expect to get different results because I'm on a different machine than him. So I expect that my times are going to be less than what his times were, but we'll find out. So he had a 100K benchmark and a 1 million benchmark, and I don't know exactly how he constructed this test, but let's say that he constructed it in such a way that the number of inputs matches the number of reference values. So 100,000 for each and 1 million for each. That's what we're going with here. And then what we're going to do is we're going to go through the benchmarks, and for each of them, we're going to generate the size of inputs, and we'll call this inputs. We're going to generate these random numbers in these lists. We're going to call them inputs and refs. So is that the same thing? Yep. I'm going to call them inputs and refs, and then we're going to run my function on them. And we're going to have to use the timing function as well. So what is my count? Here we go. We're going to take the count function that I created, and we're going to plop this in here, and we're going to say we're going to count the number of refs and the number of inputs. And really all we want to do here is time this. So I'm going to go look. I don't actually know what there's a console.time that gives you, we'll just, he was using, I think milliseconds is good enough. He was using a high resolution timer I haven't gone through console.time on the channel, and I don't really use console.time. So let's actually go through, let's use console.time that gives us high resolution timers. So, So I'm going to look for console.time. By the way, feel free to comment with questions or off the wall comments, whatever. We're just hanging out. There's no rush on this. There's nothing that we actually need to get done. Oh, this is, what? The letter L? Okay. MDN has changed. I can't say that I don't like it. It's just, very different. Okay. Starts a timer you can use to track how long an operation takes. Console time end. Okay, label. Time end, stop the timer and get the output to the console. All right, so let's try this. Let's do console.time, and we give this one a label, and we're going to call it binary search. Now there's a trick here. I'm going to reveal this in just a minute. There's a trick to why I think my numbers came in so low. Or I guess maybe saying there's a trick to it is not the, but I'm going to make one small change to my code that's not really a change to the algorithm at all. And I think we're going to see that my numbers drop significantly between two runs. I could totally be wrong about this. Okay, so we're going to do binary search and then time end. Okay. And I suppose, yep, I think that's what we want to do. So let's go ahead and run this. And then a lot of logs there. Seems like too many. Let's do this. Let's do blah.txt. Okay, I'm not sure what's going on. Let me see. So this, what I'm suspecting, let's see, input values, reference values. What I'm suspecting is that the console.log itself is what makes it take too long. And I can't imagine that he could have possibly run this with the console.logs in there based on what we're seeing right now. Or his test was very different. The number of input values and reference values was quite different based on his test. But he's not here for us to ask. So let me just look for any console.logs. I think oh, there we go. Let's comment out a few more. Comment out. Okay, so now all the console.logs have been commented out. Let's try this again. Okay. No such label default. Ah, yes. All right, so I guess I need to apply the same label. All right. So this is surprising to me. It actually ran even slower on my machine, which is the M1 Max. So I'm not sure how he did the test, but let's just bring his results back over here. But my test ran faster on his machine than it's running on mine, and I did get rid of all the console.logs, which is what I suspected would be why mine was running so slow. But there was obviously way too many console.logs. That was not going to ever finish with all of that. I wonder how many gigabytes we managed to put out there in that blah.txt. And only 89 megabytes. Slow disk. Okay, so now I want to run his code. I'm going to copy his code over because I have to benchmark this myself and see that, yes, in fact, my sophisticated solution runs significantly slower than his less sophisticated solution. Let's see. And, far simpler. But this is often the case when you're doing profiling of things. The benchmarks don't necessarily turn out the way that you'd expect. You always want to benchmark before you benchmark. You want to make sure that you actually need an optimization, that something's actually wrong before you try to clean it up, because what you'll find is that you often end up with a slower solution than what you started with. I've had this happen several times, and I've been criticized before when I was much younger for trying to basically take care of a problem that didn't exist. Because we assume, oh, I'm going to loop through a million things. That's my rule of thumb is don't ever optimize anything until you're over 10,000. Let me rephrase that, until you're over 9,000. And I'll read those comments in just a second. But sometimes you can do something 100 million times and it's not slow. So my rule is definitely don't try to optimize until you're over 9,000, over 10,000. But just because you're over 10,000 doesn't mean that you need to optimize. So let me check these comments. Performance.now, what is that? Duncan does not work at Google, no. Josue, what's up, my man? You may want to use performance.now. I guess console.time does a similar thing. I have never heard of performance.now. Let me use Google on that. Performance.now. Can't be reached. Nope, doesn't exist. Not a thing. You lied. That's one of the problems with adding all these new TLDs is searches that used to work don't. Okay, performance.now is available in web workers. Time origin. Window context. Oh, Oh, yeah, I like this one better. Okay. Up to microsecond precision. Yeah, I like that. Thank you. I like it better. I like it better because you have more control. But I do like, when you're dealing with multiple asynchronous things happening at the same time, I do like the idea of console.time, because that will help you track things that are going on at the same time, but at different rates. But so thank you for that. That was useful. Well, I don't know if it was useful yet because I haven't used it, but I think it could be useful, and I appreciate it. All right, so I'm going to, this is AJ count. I'm going to rename this one to AJ count. So we're going to benchmark his, and then I'm going to make a couple of small changes to mine to see if I can't significantly increase it. So this is Duncan count. Okay. All right, we're just gonna see my. Okay, maybe previous matches plus plus return previous matches. No, no. It'll be interesting to see if the performance were to change if I flip this to a for each. So here's the thing. This is my rule for a reducer. The rule for a reducer is that it must be a lossy aggregation, which means that you must use the input values. This is being used for a side effect, right? Because previous matches is never actually part of the value that's being dealt with. So we have score here. So score is never actually being used as part of the calculation. So this is not a valid reducer because a reducer operates on its inputs to produce a lossy value. And what I mean by that is the canonical example being adding numbers together. If you have 10 numbers and you add them together, you get an aggregate result. But you cannot tell from the result what the component parts are. So that is my rule for a reducer. Josh, I know that was only 30 seconds or so, probably isn't worth having a highlight reel, but AJ's rule, the law of AJ's law of reducers. Yeah, AJ's law of reducers. Let's clip that one. If anybody else has a better thought for that or follow-up question, let me know. Epic Gaming PC. I don't know. I'm kind of miffed though because I've got the M1 Max Pro Plus. You know, you can't get faster than this. It's not possible. Well, I guess if you're talking about single core performance, you could have faster single core performance. Anyway, so yeah, so this is Duncan count. So let's do this. We'll do the AJ count right here. And then we're going to do the Duncan count, which I'm actually going to call for each because it's not actually a reducer. It's abusing reduce to get the side effect of carrying a value. Although I would be interested. I actually am. We're going to put this here because I am going to hate it so badly if the performance comes out to be different. Oops. So we're going to do Duncan count, and then we're going to do each count. So I'm going to copy the Duncan count. The other thing is that with benchmarks like this, you never know how much of it has to do with just the code getting hot, because you're not running it in situ, you're running it in a contrived situation, and the JIT optimizer is going to optimize differently when you're running a benchmark than it's going to optimize when you're running in situ, as it were. So we're going to do this. Let previous matches equals 0. It won't surprise me too much if the reducer actually does have a performance boost because of basically JIT optimization reasons. Just little things that you can't predict. So we're going to get rid of that 0 coming in there, and we're going to get rid of this here. And this is how you know it's not a reducer, because I functionally changed nothing. I just switched this to a for each, and none of this inside of here changes. Nothing, everything is the same. So the value that was not actually being used as part of the reducer. It was not actually aggregating anything. Okay, so we'll do the each count. I will not be surprised if the each count is a little bit slower than the reducer, but not because the reducer is inherently faster, just because there's a toss-up. If you do a plus plus versus a minus minus, if you count forwards versus counting backwards, there's just all these little things where you don't know. It's a coin toss as to how the just-in-time compiler is going to choose to optimize the code based on that run in the benchmark, which may be different than the way that it optimizes it in the real world. But we'll go with this. Okay, what did I do? Answer equals count. Answer equals, oh, we need to do AJ count on this one. Okay, let's see what we got. Oh, wow. I actually am surprised that the for each is so much faster. Um, wow. That is quite interesting to me. Huh. Wow. I did not expect that. I expected it to maybe be a toss up. I did not. It must have something to do with allocation and deallocation because I was thinking that the performance in the jet optimizer might be around the allocation because it's a reducer. You can count on the memory being in the same space pretty much. But I guess there's just more internal machinery. But this is pretty much mind blowing that changing it from a reduce to a for each had a 4x improvement. And again, this does not mean anything for the way that it would operate in the real world. This is just in the benchmark, the JIT optimizer, for whatever reason, chose to optimize it differently. It's the same code. It's doing the same thing. If you were to compile this to a C program, rather than being JIT optimized, if this was compile time optimized, you would expect these results to be identical. But that's quite interesting to me, and it's really interesting to me that my binary search is so slow. And I'm going to guess that it's because it isn't being JIT optimized in the same way. If I changed my if to an if else, or I mean, I just don't know what. When you start hacking the JIT optimizer, you've gone too far because you cannot guarantee reproducible results from one iteration to the next, because you might upgrade from node 14 to node 16 or node 16 to node 17 or whatever it is, and you get the new version of V8 that has teeny tiny performance tweaks this way or that way, and you could just blow yourself 5x one way or 5x the other way. You don't know. And so as a general rule, I stress that you should not performance hack on JIT optimizer stuff. I did not use the arrow function. Oh, that's right. The M1 Ultra exists now. So the M1 Max Pro Plus is not enough. But I don't have the money right now. We're buying a house. I got a down payment to deal with. I don't have the money. And then I have to buy a shed to replace this garage, because the garage we're going to use for cars in the house, So if it's between the shed and the M1 Ultra, shed wins. Okay, but I'm gonna try to hack my binary search, because I know I could. Well, I don't know that I can make it faster, but I have some suspicions of how I could make it faster. So, essentially, because of this specific problem, the way that it's doing the binary search, I know that we could optimize it. Instead of starting from the middle, we know that we're looking for numbers that are less than or equal to, so we can always start from the left. So that's a really quick optimization. So we're going to take the AJ count, and we're going to make another one, and we're going to call this AJ count left. And then all we're going to change about this one, and I'll be interested to see how much an improvement this is or isn't, is we're going to get rid of this middle number. So we're going to get rid of M, and instead of having I start at M, we're going to have I start at the left, which is 0. So let's just do it that way. And that's the only thing we're going to change about this one. Everything else is going to stay the same. But I suspect that just doing that change will have a significant impact on the run speed of this program, because we're looking for numbers that are less than or equal to. So if we start from the left and we move towards the middle, we're going to cut out basically, well, I guess just one jump, but over time, I think it'll make a difference. We'll find out right now. And there's a similar hack that I want to make that's a little bit more complex than that. So I'm going to say binary search left. And for comparison, we ought to try binary search right, because again, you don't know how these optimizations are going to turn out when you're looking at JavaScript. Okay, so left. Look at that. Look at that. Binary search left is faster than the reducer. Okay, I think I can make one or two more changes and get that to halve or maybe even quarter. No, I did. That was Duncan's code. I copied Duncan's code, so I did not put the arrow function in there. Sorry, I didn't explain that. We were testing Duncan's reducer versus my binary search, because his reducer was faster than my binary search, but then my for each was faster than his reducer. But I would say try to use array methods. Again, usually you're not dealing with performance when you're working in JavaScript, but try to use array methods that are semantically correct. Follow AJ's law of reducers. Reducers are for aggregate values that operate on the inputs to produce a lossy output. That is it. Okay, now I'm going to create another one of these, and I'll put these on a gist, just so we've got all of them. I'm going to give you a link to the gist that we're going to have for this. By the way, feel free to ask questions. It can be off topic too. It doesn't have to be on topic. I don't want anybody to feel like we're constrained here. This is AJ Unchained. Alrighty. Okay. I'm going to call it double left. So what we're going to do now, so we're sorting all of the inputs. I'm going to map the reference values. So let me get rid of all of this. We're going to do a little fun little thing here. So I'm going to do, and because I don't believe that you should swap types of things, I'm going to create, we're going to call it refsmap, and this is going to be refs.map. And also you can sometimes, again, I don't recommend this type of performance hacking, but sometimes you can switch, and you just won't know until you do it. But sometimes you can switch from a function for each to a syntactic for each and change again. So I'm going to abandon this for a second because I'm really curious. Let's go to our each count. And then I'm going to change this from being each count to being for count. And I want to see how much faster it is again. So we're going to call this one for count. Sorry, I'm switching things on you. And then we're going to do for let's, what is it? I forget. Score of team B. Is that how it's going to go, like that? I think maybe. We're going to get rid of this one. We're going to get rid of this one. Is that right? I think that is. Also, he's making a copy here this way. I don't know if that's more costly. There's all sorts of things that we could check out. Does this syntax sugar cost more than just calling .slice? I bet it will, because it's more complex. There's a number of nuances to using this type of syntax versus just calling .slice. Could be completely wrong. Slice could be slower. You never know. You can just take guesses and you can check them. But let's just see before I even do the next one. We're going to pop out the for. Okay. And I just want to see how does for compare. Oh, look at that. So for is ever so slightly faster than for each. So we get just a small gain, just a few percentage points. Again, please don't performance hack. This is purely for fun. There are situations where you do need to actually performance hack, and you'll experiment with these things, but then you have to run all of your benchmarks whenever you're changing versions of the JIT compiler. If you're going from V8 one version to V8 another version, if you're testing it on mobile Safari versus testing it on Android versus testing it on Windows, all of these things are going to have an influence on how that JIT ends up getting compiled. Oh, it'd be interesting to see how the performance between JS and Rust would differ. Actually, I think that Duncan did that. Let me see if I can find, let's see, Rust code. Yeah, the Rust code was significantly faster. And he did a couple of, he reduced the allocations in the Rust code. So he was able to get it to be quite fast. Even with my bad implementation. I think that his implementation was quite good, and he took advantage of some things that I had not known about. Basically, there's a special sort function in Rust that I think the purpose is it guarantees fewer allocations, but it doesn't guarantee consistency in equally weighted elements. So let's say, for example, you had an object and it had a calc value function, and the object could return 5. And it was possible for another object to return 5. Well, when you sort them, ideally, you would say, well, these two objects, since they were already in the correct order, we shouldn't swap them even though their values are the same. And so there's a function that does not guarantee keeping the ordering, and that one runs slightly faster than the one that would do the thing that you would expect, which is intentionally not swap similar or values that are weighted the same by whatever metric you're using to do the sort. So there's a couple of things there, but I actually think we might get performance just as fast as Rust, because remember that Node.js will JIT down to assembly. So that was one of the neat things about V8 when it first came out that nothing else was doing, is it JIT all the way down to assembly. So let's see what happens here. Well, I was going to do my double left. That's what I was working on, right? So we're going to have this refs map. Okay. So what we're going to do is we're going to take the ref value and the index, and we're just going to return an array with the ref value and the index. And I'm not going to do anything else, and I just want to see what happens because just this alone is going to take up extra time. So let's see what the double left is versus the left just from this. I'm just pure curiosity, doesn't matter at all. And that's what all this is right here. So my double left is significantly slower because it has to do all of these allocations and stuff. I wonder if I could make it faster. I wonder if I could do something differently. Because that just adding in that one function makes it way slower. And it's consistent. It's consistently slower. Yep. Okay. But so what I'm doing, again, in performance hacking, you never know how it's going to turn out. What I'm doing may turn out to be the same, because the benefit that I get that I thought was going to give me the big boost, the cost of creating this mapping of references to index may just not be worth it. But anyway, we're going to go here. We're going to do Refsmap.For And what this is going to do is, so we're going to be able to then sort this. Let's see, Refsmap.Sort. And then what we can do is A and B, and we want to make sure that A sub 1 minus B sub 1, which is the original value. What I've done is I'm creating this tuple, which there's possibly a better way to do this tupling, but this tuple of ref and index allows me to have the original position, so that way I can sort this. So now I'm doing a bunch more work because I'm iterating over it once to create a map. Then I'm sorting it. But now that it's sorted, I can actually iterate over it much, much quicker. I think that it'll be quick enough to make the gains worth it. Maybe, we'll see. Because what I can do now is I can say, instead of left being something that we assign here at 0 and leave it at 0, we can now pull left out up top, because now we have a guarantee that every left value will be equal or greater than the previous left value. So I'm going to call this tuple now, and let's see, I'll call it tref for tuple ref. So ref, it'd be nice if we had tuples in JavaScript. That would probably make it run a little faster, because it's probably allocating more than it needs to. And then sub-indexing, of course, is going to have a cost that a tuple wouldn't have. All right. So again, tref, there we go. So it might actually be more cost effective to pull this out rather than to sub-index it twice. Again, this is something a compiler should compile away. The compiler should see we referenced this twice, so the compiler should actually hoist up the assignment of this value and then use that in both places rather than actually extracting it twice. We don't know what it's going to do. But then down here, let's see, instead of pushing I plus 1, what we'd actually push is tref 1. Well, not push, but we'd swap this out to be tref 1, which is the original index, to be I plus 1. There we go. That's what we need. So now And this could be faster because instead of pushing, if the array gets bigger, this is another thing. This would be very interesting to see what this changes. If we pre-allocate the array, is it faster? Rather than having it push, 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 push. And that's something that we could do too. This is something that you hardly would ever see in JavaScript, but I am interested. There's just so many things I'd love to test here and just see what the difference is. Let's go with our fastest implementation so far, left. And I'm going to create a new left that is count left alloc. And we are going to allocate the outputs array at the full size at the beginning. So I'm going to do this, new array refs.length. And that should allocate an array that's this size ahead of time. So I'll be interested to see how that one turns out. So we've got a couple new ones now. We've got count left, alloc. So we're pre-allocating the array. And then we've got our double left, which I think, we'll see if the implementation is right or not. Okay, whoa. That is unexpected. That's slowed way down. That's really interesting to me that it's slowed down so much. Oh my goodness, this is insane. That's not even possible. So pre-allocating the array caused it to go slower. Let's see if that's consistent, because that could be roll of the dice. Okay, no, it is consistently slower if we pre-allocate the array. Who could have imagined that it would be slower if we pre-allocate the array? That's just insane. Okay, let's try this a different way though. There's different ways to allocate arrays in JavaScript. Let's say that instead of doing it that way, let's say that we allocated it this way. So basically what we're learning is the JIT is better at looping over 1,000,000 items sequentially in a row and adding one than it is at doing a binary search on 1,000,000 items. So just think about that for a second. In JavaScript, it is faster to iterate over 1,000,000 items, which is going to take 1,000,000 iterations, than it is to do a binary search, which is going to take, maximum 16 iterations? So isn't that crazy? Oh, the test case is failing? Sorry, I didn't even see that. Thanks for pointing that out. Let's take a look and see what the test case is failing about. Pass, fail, pass. Let me check on that. So pass, test for each. This might have the wrong values in it. Let's see. Thanks for pointing that out. I wasn't even aware of that. Let's see what it says. 2.3, 2.2. Interesting. So this getting faster? Maybe. It did. It's about a millisecond faster. Well, okay, maybe not. It seems a little bit faster to allocate it with .length rather than new array. Again, weird. So I'm going to guess that the reason the test is failing is that something about my logic is wrong. Now, it was passing before, I think. But let's see. Inputs, 1, 2, 3. So less than or equal to 2, less than or equal to 4. So this should give us 2, and this should give us 3. So the test is correct. It is failing because there's something wrong in my logic. I'm not going to debug that right now because that ship has sailed and I'm on to the performance benchmarking ship. But I obviously have an off by one error. I'm probably I'm just not doing something right. So I'm going to try a couple more things and then I'm going to end the stream and then maybe move on to something else. I will answer other questions. Do you think about cache hits and misses when you optimize code? What type of cache? I do not think about level 1 or level 2 cache, no. I do think about cache that I'm directly in control of. I don't optimize code like this. I don't work in assembly. In order to optimize code, you're either doing guess and check, which is what you're going to have to do in JavaScript unless you're one of the people that worked on V8, right? Or you are going to be really familiar with compilers and assembly. I mean, there's certain algorithms. We know that the algorithm in of itself is faster or slower than other algorithms. But what algorithm is faster in theory and what algorithm is faster in practice are different beasts. And in the last session, I gave this example of there's a particular multiplication algorithm that beats out the big O notation for the naive approach that is usually used. But it only becomes effectual when you're dealing with really, really large numbers. So I think it's an algorithm that's sometimes used in big int multiplication if the ints are known to be on average sufficiently large, but it generally isn't worth it because it's easier to optimize the naive implementation to be faster on the hardware than it is to write the software to require fewer CPU cycles, if that makes sense. But let's just try this. Ref equals tref 0. Again, I'm just going to take a couple of shots in the dark to see what happens. This was my double left. So is this seriously correct here? Was this my double left? Yeah, this is my double left. So left is moved up here because left is always going to be moving towards the right no matter what. I'm surprised that that doesn't have more of an impact. I understand that the overhead is quite a bit more. Okay, what were the previous runs of this? So that probably did about nothing. Okay. Oh, and look, 4 actually is slower this time. So to some degree, what? So the 4 is now consistently slower? Yeah. I don't know what changed there, but now the 4 is consistently slower. So this is another thing. You add more code for the JIT optimizer to try to figure out how to optimize it, and it's going to optimize differently. So here we did not change the algorithm. We added new algorithms that are running differently. And the new algorithms, so in order to properly benchmark this in a true micro benchmark, you would actually need to run these independently so that they're not running. You'd have to have the process start up, run the one test, have another process start up, run the next test, because simply changing the code is causing the results to be different, even when the code that was changed is not the code that has the affected performance. So this is interesting to me. For each has the best performance. So let's just double check at this one more time. Let me see if I got some other questions I can answer here. Could be argued that benchmarking code that doesn't work correctly is pointless because you're getting the code to work correctly is likely to change the performance. Yes, I agree. But at this point, it's just for fun, right? So if I were able to make a significant difference to the code in its performance, then I might go back and see if I can fix the little off by 1, which I think we could do with the original output. Maybe I'll go do that just for fun afterwards. What was I going to change here? I was going to try something. What was that? Oh, I was just going to look at that for each. Okay, so imagine here. So remember, refs is 100,000. So let's just get rid of each count. All right. So it's doing a shallow copy of team B, which could be argued as what I should be doing. Okay, so one other thing that I wanted to try. Oh, and also using const, again, don't do it, but using const could change performance. Ostensibly, it should make performance better, but in reality, I don't know. But let's just see if we change this from that to the other, if that makes a significant difference on the reducer. It'll just be interesting to see. Doesn't look like it did. Looks like it's within a millisecond still. I do want to try just changing some lets or vars to const and just see what happens here. So do we have any vars in here? No, we just got the one. We can change that to a let. That's fine. Now I'm going to senselessly make variables constants just for fun. Let's see. I don't think I have any variables in here to make constants. Okay. All right, so yeah, this is so weird. And the difference between the naive implementation, which takes 70 seconds or something, and the implementation that is pretty naive, but works much faster. Let me go double check on this. This is what I wanted to double check on. Yeah. It's just a matter of sorting them, but you're still doing, you actually don't change the big O in doing this, because you still have to count possibly all the way to the end. When this runs its reducer, it has to go over all of team B, which is 1,000,000 long, and it has to do that. And then it's still going over team A, previous A index. Oh, this is actually, wait. No, this is essentially doing the same thing as my binary search, more or less. Sorry, I wasn't paying close enough attention to this. So this is not just a naive implementation. This is a smarter implementation, because the previous A index starts at 0. This is basically my left. So my left is starting at 0. His previous A index is what he calls it, starts at 0. And so his previous A index is always moving from left to right. So this is actually kind of the same thing as my binary search. It's just a little, it's a little bit, better for this particular scenario. I think that if you were to write this in C, I think that the binary search would be faster. But in JavaScript, because you're having, it's easier for the JIT optimizer to optimize that you're incrementing along an array than it is for it to optimize switching back and forth between locations in memory. So even though you're doing fewer memory accesses, it's faster to do more memory accesses, but in sequential order. And that is why I think that this one goes faster. But yeah, so he actually is using the same trick I'm using, where he's keeping track of his left value and making sure that he pushes his left value forward. And then he's keeping track of his match value and then making sure that he's adding on to that. So I wasn't paying close enough attention before to understand that that's what he's doing here. And then the cache is, I don't think that he actually gives back the right result in this. I could be wrong, because team BI cache score previous matches. I think that this ends up being in the wrong order, or does it? No, this ends up being in the right order because he's going over team B again. I could probably apply this technique to my binary search. In fact, I want to do that. So that's the last thing I'll do. I'll take my fastest binary search, I'll apply this technique, and I'll see if I can get the same results that he's getting. Because this is going to cause less duplication than what mine does. It's more memory accesses, but it's less allocations. Okay, let me catch up on comments here. Can we change the stream title to AJ versus Duncan? Yeah, we could. But I don't think there's any need for that. Or maybe there ought to be. Yeah, we could put two faces on here. Well, Josh, we're thinking about changing the stream title as per the suggestion here to AJ versus Duncan, but then we'd have to get Duncan's face to slap on the thumbnail. But that's okay. We did that with chi-space. So yeah, I think that's a great suggestion. Way to go, Elon. All right. So I two more things then. I'm going to try the same caching strategy. I'm also be interested to see what if we change this from a const to a let, which shouldn't make any difference because it's a variable, so there's no way to optimize that away. But just pure curiosity here. Pure curiosity. So let's see. What if we run this again? And this was Duncan's reducer. Did we take it down? What? No. What? No. 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 Hold on. No, we only changed this one. It couldn't have possibly changed that. What? 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 What did we even do? Did I seriously just change it from const to let? No, what? The previous run was... Oh, okay. I was looking at the wrong value. Okay. I was looking at this one, and I was thinking, there's no way. I was looking at the wrong value there. Okay. So interesting. This... What? That also doesn't make any sense. So let me see if I change this back to const. Again, I would hate for this to actually prove to make a difference. Okay, this is just completely random. All right, that's what I would expect. Yeah, because since this is a variable, declaring as const should have zero difference because you're still doing the same number of accesses, the same number of writes. It's not actually a constant. You're not actually preventing writes from happening, so therefore the speed shouldn't change. So looks like the changes we saw were just in the noise. But I'm going to go ahead and take this and apply it to my best binary search, which is my single left. That still blows my mind that pre-allocating the array causes it to take significantly longer. That just blows my mind consistently. Okay, so here's our left. All right, let's put our cache here. And we might get the same or similar. We might be able to beat him out using his caching strategy here. So the caching strategy was, let me go back and take a look at that. The score is previous matches. Okay. So score, so I think it was the reference value is what we were looking at there. So I think it was basically, where's my count left, my single left? Count left out, count left. Okay, I think what we're saying here is right down at the bottom. Let matches equals I plus 1. Hopefully just assigning something to a variable won't make much of a difference. It seems that those things are not making too much of a difference. But then ref is equal to the sum total. Let's say total. Let's call it total. All right. So we're going to do the same thing. We're not going to do the output. We're just going to do ref. Okay, so we're not doing output here. And we're going to make a copy of our ref values. So we're going to do let's call it orefs. Orefs equals refs.slice. And then we're gonna sort our refs as well. So we also could get a difference using this function once versus using it twice. That could make a difference. It could optimize it differently. Gosh, there's just so many things that you just don't know what random difference they might make. So down at the bottom, we're going to go through our orefs. this it certainly will go to support the theory that two heads are better than one, I think, no matter what. And just experimentation. All right, so orefs, then we've got val, and then what is it? So outputs.push cache val, right? That's ref. Okay, so let's call it ref. So this should be correct. All right, let's see. Let's see if this speeds it up for us. Oh, it made it slower. What? But then this one got faster? What the letter L is going on? Hold on. Okay, this was definitely slower before. Now this one got faster. Significantly faster. Okay, let's run this again. Is that real? Okay, by making this one slower and making no code change to this one, we made this one faster. Let's double check that again. Let's make sure that I've got the right string output in the right place. Called, okay, left alloc. Left alloc. That just, left alloc. I did not change this one, correct? I did not. I did not change this one. I don't even know. All right, now I want to do our, what was it, sort by? Sort, where's the sort function here? Let's replace my sort function with the same one that he's using and see if we don't get an optimization just from, yeah, so he calls it sort fn. Okay, so we're going to call ours, we're going to do sort fn on ours as well, just to see, is this the right one? No, it's not. That's double left. Okay, so let's go back to AJ count left. Isn't this interesting? So wait, what? No, my fastest one now is left alloc. So I'm going to take my fastest one now, and we're going to do sort fn. And I am going to change the other one, because that one has two sort functions now. So maybe they're not being optimized or whatever, you know? So we're doing AJ left alloc, and then what was it? AJ count, AJ left. So we're going to do sort fn on this one as well. And then sort fn. So now the sort fn should be really optimized because it's being used in so many places, right? Problem is, it'll be faster towards the bottom than it is towards the top. Okay? So now, but look at the change in this. This is just crazy. Okay? So now my binary search, what? And then this one flip-flopped again. Now this one is significantly faster, and we did not change any of the code. Okay, I'm just going to end this. We're done. Using a map instead of an object for cache. What do you mean using a map instead of an object? Do you mean a JavaScript set? What do you mean by map instead of an object? Objects and maps and dicts are all the same thing in JavaScript. If you use a set or a map, it's typically going to be slower than if you use an object, meaning the specific JavaScript types. Okay, well, let me go ahead and just post this code for everybody to, shake a stick at. That was a lot of fun and a waste of an hour of our lives, but hey, we did it together. So what should I call this one? Binary football. And then we'll call the other one, I know what we'll call it AAA football. And then, never mind that the tests aren't actually working. because there's some sort of off by one error. Well, let's go ahead and add let's just add a README to this. For loop outperforms the binary search, and the optimizations have nothing, let's say almost nothing to do with the algorithms. I just want to put here, changing any code can massively change the performance of any benchmark. That's what we got out of this. Okay, I'm going to plop the YouTube stream in here. I'm going to give you all the link to this once again. We're going to close this one out, and I might just call it a night. There was something else I wanted to do, but we had a good time. We had a lot of fun, and I want to maybe I want to sleep tonight. I don't know. If I can't sleep, then maybe I'll come back down. But here we are. There's the gist of football optimization madness. But the for each, well, the for each did until we changed the caching in an unrelated function. BOGO sort wins. Actually, BOGO sort does not win in this particular case. But BOGO sort is when you just randomize values and then check to see if they're in order. Okay. Oh, and I was gonna take the YouTube link and I was gonna throw this in here. Thanks. You have a good night too. Let me just grab the YouTube link, throw this in here, and we'll call that one good. My channel. Oh, I'm live now. Y'all want to hear? Let's see what I have to say. My channel. Oh, I'm live now. Y'all want to hear? Let's see what I have to say. All right, there we go. Oops. See the video. All right, y'all. Thumbs up if you got them. Like and follow, sub, whatever, all that stuff if you want to. Have a great night, noon, day, morning, whatever it is, wherever you are. I still have half a can of Mountain Dew. I think I might just dump it in the drain. I do that sometimes because I don't know if it actually makes me stay up. I think sometimes it does. I think a lot of it's up in your head, But yeah, y'all have a good one. Thanks for hanging out with me. This was really fun. I thought this was really fun. I like these things. They're stupid, but sometimes you just got to take some time to do some stupid stuff and just see what happens. So thanks for joining in with me, and I'll check for comments one last time, and yep, no more comments. So adios, y'all.